Hi everyone, this is Ray Zhu. I'm presenting our work, Factorized Inverse Path Tracing, FIPT for short, for estimating dense lighting and materials of indoor scenes. The input is multi-view HDR observations of an indoor scene and mesh-based geometry. For each location of the 3D scene, with an example of this view, we seek to estimate emitters and material parameters. Given those estimations, the method enables applications such as view synthesis, object insertion, and relighting, where we turn off the original emitters and turn on the stove light, put a bunny on the table, and render in its novel view. Our method reproduces the fine details in material and specularity in lighting, and converges several times faster than previous methods. One of such methods is IPT, using differentiable path tracing, which alternates between forward path tracing and gradient descent steps to jointly optimize materials and lighting. In the forward step, a rendering error is calculated after path tracing, and a backpropagate step updates the emission and material parameters along all the paths. While IPT works well for simple material models, its variance reduction becomes expensive when the scene gets complex. We propose to factorize the rendering integral into BRDF terms in green and shading terms in orange, so that shading terms can be pre-computed with cheap variance reduction tricks, and then BRDF terms can be efficiently solved without having to jointly optimize all the parameters in each step. Specifically, the integral can be rewritten as a linear function of diffuse and specular reflectance, KD, KS, and diffuse and specular shading terms, LD, LS, 0, and 1. You may notice specular shading terms still depend on BRDF parameter sigma. In order to pre-compute specular shadings without knowing sigma, we bake a set of specular shadings with predefined sigmas. Later, given an estimated sigma, we efficiently interpolate between the baked specular shadings to get the final shading. Based on the factorization, we can efficiently pre-compute shadings offline. Then we fix the shadings and optimize emission and BRDF. After that, we can go back to rebake shadings based on updated material lighting and alternate until convergence in limited steps. Comparing to IPT, we converge much faster and observe reduced variance in estimations. Here are the detailed steps of our pipeline. Firstly, to initialize the shadings, we pull the input views onto a volumetric surface light field, which serves as a radiance cache similar to NURF. Querying it allows us to bake the initial diffuse and specular shadings. Given the initial shading, we solve for BRDF and emission. We use a newer representation of materials. For emission, we optimize without an emission term, but with an emission mask alpha with sparsity constraint. Surface emissions are then extracted in closed form by thresholding on estimated emission mask alpha. Our emitter estimation is significantly faster than joint optimization of emission and BRDF parameters, and suffers less from the ambiguity between material and lighting. Once the initial BRDF and emissions are estimated, we seek to refine the shadings with global path tracing. To do so, we extend the path for low roughness surface until it hits a diffuse or emissive surface, which compensates view-dependent effects in the light transport that might be missing in the volumetric surface light field. We alternate between BRDF and shading refinements until convergence. Overall, FIPT significantly improves BRDF lighting reconstruction. In this example, we preserve the fine texture of the floor and accurately estimates the highly specular mirror. As a result, we produce better rendering under novel lighting, where the details and craft reflections are well preserved with our method, highlighted by the mirror and the metallic range hood in the results. For evaluation on real scenes, we capture two scenes with around 200 HDR images each with linear response. We test all methods in light editing and compare against pseudo-ground truths. As we may observe here, our method is the closest to the reference, with shadows under the desk and highlights on the floor decently reproduced, with minimal artifacts thanks to reduced variance. Please visit our website for more details and resources. Thank you.